Okay guys, in this video we are going to talk about the third law of thermodynamics, and we are going to do entropy changes for chemical reactions. So the third law of thermodynamics, basically what it does is it sets the scale for doing entropy calculations by defining the lowest possible entropy value. And so the statement reads, every substance has a finite positive entropy. The entropy of a perfect crystalline substance is 0 at 0 Kelvin. First off, at 0 Kelvin, atoms and molecules are not moving around. They have no kinetic energy. Okay? So there's no entropy associated with the velocities of the molecules because their velocities are all 0. They're not moving. And then the other thing about a perfect crystal is that in a perfect crystal, every atom occupies a precise lattice position. So you can imagine then that their positions are completely known. So there's only one way to rearrange or to arrange the atoms and molecules within a perfect crystal. Therefore, there's only one possible microstate, and if you use that statistical definition of entropy and you plug in 0 for the number of microstates, you get that the absolute entropy is 0. Okay, so this third law is perfectly consistent with the information theory definition of entropy. In practice, not all substances, when they are cooled down to very low temperatures, they don't all form perfect crystalline substances. There can be defects, and then there can also be, just depending on the nature of the substance, you'll get just not a perfect crystal, and that leads to what we call residual entropy. We are not going to really have to worry about that at all, so I just sort of threw it in there. We are going to be interested in looking at the molar entropy of different substances. So this S subscript M has units of joules per Kelvin per mole. The entropy, the absolute entropy for 1 mole of substance. A couple of rules to keep in mind. The molar entropy depends upon the phase. And this is a very useful thing to keep in mind. The molar entropy of gases is typically much, much larger than the molar entropy of its corresponding liquid, and that's much greater than the molar entropy of a solid. Not much greater, but greater than. So there's a big difference in the absolute entropies between liquids and gases. Gases always have a larger molar entropy. And then liquids and solids, liquids have the higher molar entropy than the solid. So this is very useful for eyeballing the sign of delta S for a chemical reaction. And I'll give you an example of that before the end of this video. Another aspect of entropy is it increases with the molar mass of whatever substance you're talking about. So the bigger the molecules involved, the larger the molar entropy at a given temperature. Likewise, the more flexible the molecules are, that is, the greater the ratio of single to double bonds, the higher the molar entropy. If you have a very rigid structure, I don't know, like an aromatic ring or something like that, it can't move around a lot. It doesn't have a lot of flexibility in the structure, and so those rigid structures have larger entropies, larger molar entropies than more extended structures. So here we have just a simple, this is just a conceptual problem. Arrange the following molecules in order of increasing standard molar entropy. The one with the largest molar mass is going to have the larger entropy, so that would be the CHCl3. Is going to have the largest entropy. The smallest one will be the CH3Cl, the methyl chloride, and then the dichloromethane will be in between. Okay, we have the largest molar mass, the smallest molar mass, and then the in-between one. For the second part, estimate the sign of the entropy change. Notice that we've got two gases in the reactants and no gases in the products. Okay, so this reaction is essentially consuming gas. Gases have larger entropies than liquids, and so we would predict that delta S for this reaction is going to be less than 0. On this slide, we are looking at how to calculate or measure the absolute entropy at a finite temperature for a substance. Okay, so we're interested in the standard molar entropy, and you can arrive at that using this scheme here. So what you do is you start off with the absolute entropy at 0 Kelvin. And if it's a perfectly ordered crystal at 0 Kelvin, this number would be 0, or this may be the residual entropy. And then you want to get up to temperature T, and so we've got a term here for heating up the solid. So this is the molar heat capacity of the solid. It's a function of temperature in general. You divide by temperature, and you integrate from 0 Kelvin up to the melting point. Then we have a term, this is the entropy change for melting that solid. Once we're at the liquid state, we then integrate over the heat capacity for the liquid, which could be a function of temperature. We integrate that divided by the temperature from the fusion temperature to the vaporization temperature. So this is the entropy change for heating the liquid. Then you may need to boil the liquid, so this is the entropy change for vaporization. And then to get up to whatever this value of temperature is, you would need to heat up the vapor phase. And so this is the heat capacity of the gas divided by temperature. And you would integrate that from the boiling point up to that final temperature. Now, if the final temperature is between the fusion temperature and the vaporization temperature, well, then you wouldn't include these extra terms, and you would make this whatever that value of T is. It just depends on what T is. So you may need to go all the way to the vapor phase, or you may need to stop short if at that temperature your substance is a liquid. In one of the example problems, we're going to make use of this Debye model, where which is essentially, it comes from statistical thermodynamics. It's a way of it's a model for calculating the heat capacity of a non-metal solid at low temperatures. The result of the Debye model is that there's a temperature cube dependence to the heat capacity. So you can, in principle, put that model into right here for the heat capacity of the solid. Here's some graphics depicting those figures that we were looking at. So what's being illustrated here is the heat capacity divided by temperature as a function of temperature. And so here we've got the Debye approximation, right? It's that T cubed divided by T, so it's a T squared in this figure. And then what you're looking at here is the heat capacity divided by temperature for a solid. At this point, you've got the melting point, and then there's a jump in the temperature, or a jump in the heat capacity. So here what you're doing is you're heating up the liquid. Then there's another jump in the heat capacity as you convert from the liquid phase to the gaseous phase, and then this curve represents the heat capacity divided by temperature for the vapor. What we're looking at down below is basically the integral, the accumulating integral of this heat capacity divided by temperature. So the point right here is given by the area under this curve from there to there. And then the point here would be the integral under this curve from 0 to whatever this temperature was. So you're accumulating the area as you go. And so what we see is that the entropy of the solid increases until you get to the melting point. Then you get a big jump in the entropy as you go from the solid to the liquid state. It's a discrete jump. Then you're heating up the liquid. You see that the entropy rises as you increase the temperature of the liquid. And then you get another big jump when you vaporize the liquid to the gaseous state. And then you're basically just heating up the vapor. Notice that it's always increasing as you increase the temperature. So molar entropy always increases as you increase temperature. Well, so here they want us to outline the calculation of the molar entropy for nitrogen gas. I'm just going to walk us through that long formula. So to calculate the molar entropy of nitrogen gas at 25 degrees Celsius, you would start with the molar entropy at 0 degrees Celsius, which would be not 0 degrees Celsius, 0 degrees Kelvin. So this would be 298 Kelvin. Then what you would do is you would add a term for heating up the solid. So you would heat it from 0 Kelvin up to the melting point of nitrogen. I'm just going to call it T fusion. And what you would include here would be the molar heat capacity at constant pressure for the solid, which is a function of temperature, divided by temperature, dt. So this is heating up solid nitrogen up to its melting point. Then what you're going to have is a phase transition. You're going to have the enthalpy of fusion divided by the fusion temperature. So this first integral corresponds to the area underneath this portion of the curve. Then this part corresponds to that jump. Now we're going to heat up the liquid, and so we're going to have another integral, this time from the fusion temperature up to the boiling point. We'll call it TB. We're going to integrate the heat capacity now of the liquid, which is a function of temperature, divided by temperature dt. So this integral represents the area beneath this curve here. Sorry, the area beneath this curve. When I was pointing down here, I should have been pointing up here. So this first integral is the area under this curve. This term here corresponds to that jump. This integral corresponds to the area under that curve. And then now we're going to do the enthalpy of vaporization divided by the boiling point. Okay, so that corresponds to that jump right there. And then finally, we will integrate from the boiling point up to 298 Kelvin. And we're going to integrate the heat capacity of the gas, which is a function of temperature, over T dt. And that's going to, let's say 298 is right here. That would be the area under this curve up until you get to 298. Okay, so that's what's going on in this formula. This is a problem involving the Debye model. So you've got, they tell us that the molar constant pressure heat capacity of a certain metal is 4.2 Kelvin, and the value, or at 4.2 Kelvin, it's 0.43 joules per Kelvin per mole. They want us to calculate the molar entropy. So the Debye model was giving us the heat capacity of a solid as a function of temperature is equal to some constant A, T cubed. So what they're giving us is the value of the heat capacity at a particular temperature that allows us to calculate A. So it's going to be the 0.43 joules per Kelvin per mole. divided by 4.2 Kelvin, and we're going to cube that. So I'm getting A is 5.8 times 10 to the minus 3. That's going to be joules per Kelvin to the 4th per mole. And then what we want to do to calculate the entropy at 4.2 Kelvin is we'll take the entropy at 0 Kelvin, which we'll just take to be 0, and then we're going to add into that from an integral from 0 to 4.2 Kelvin. We're going to integrate this A t cubed, that's Cp, over T dt. And so that's going to give us I'll call it Tf squared over 2. No, it'll be cubed over 3, right? It's T cubed over T, so that's T squared. The integral of T squared is T cubed over 3. Tf here is at 4.2. And so we'll take the 5.8 times 10 to the minus 3 joules per Kelvin to the 4th per mole, divide that by 3, and multiply by 4.2 Kelvin cubed. Divided by 3, and we get 0.14. This will be joules per Kelvin per mole. All right. So this is another topic related to the third law, the Nernst heat theorem. It tells us that the change in entropy for any process goes to 0 as the temperature goes to 0 Kelvin, provided that all of the substances involved are perfectly ordered. And that makes sense. If the entropy of every perfect substance is 0, then the change in entropy will also be 0. And so that's exemplified here in this problem. We're going from orthorhombic sulfur alpha to monoclinic sulfur beta. We're given the entropy change, we're given the enthalpy change for the process and the phase transition at which it occurs. They want us to calculate the entropy change and then compare this to the one that's obtained from heat capacity data. So we're going back to this idea or this equation that the change in entropy for a phase transition is the enthalpy change of the phase transition divided by the phase transition temperature. So that's pretty easy to calculate here, 402 joules per mole divided by 369 Kelvin. So I'm getting 1.1 joules per mole per Kelvin when we calculate the entropy change this way. When we calculate the entropy change the other way, it will be the molar entropy for the beta phase minus the molar entropy for the alpha phase. So we're going to get this Sm beta at 0 Kelvin minus the Sm alpha at 0 Kelvin. and then it's going to be plus 38 minus 37, 1 joule per Kelvin per mole. This right here, this is the delta S for the phase transition as T goes to 0. And according to the Nernst theorem, that's 0, so we get 1 joule per Kelvin per mole, which is pretty close to what we got for the other direction. Okay, not much to this problem. Anyway, that's an illustration of the Nernst theorem. It tells us that the delta S for any process where the temperature goes to 0 is 0. Well, in this next set of slides and problems, we are going to be looking at chemical reactions. And so you've already done quite a bit of this in general chemistry, calculating the entropy change for a chemical reaction. You use that products minus reactants approach. Here I've expressed the formula in the compact notation where the new i's are the signed stoichiometric coefficients. So these are negative numbers for reactants and positive numbers for products. These numbers here, the absolute entropies, the standard entropies, you will look these up in a thermodynamic table. Here's an example of one, and there's more values in the back of your textbook. If you look through that table, you'll notice that a few of the species, in particular some of the ions, have negative values listed for their absolute entropies. And if you've been paying attention, the third law tells us that the absolute entropy of a substance at finite temperature is always a positive value. Well, that's still true. The third law is true. However, because ions cannot be studied independently of one another, for example, cations cannot be studied independently of anions, we don't really know what the entropy, the absolute entropy, is for an aqueous cation by itself, because there's always anions around. And so what's done is the absolute entropy of H plus aqueous is set equal to 0, and then the absolute entropies for all other ions are measured relative to that value. So when you see a negative value listed for an ion in these thermodynamic tables, note that the absolute entropy is not really 0, it's just less than the absolute entropy for H+, which is taken to be 0 by convention, and it enables us to do our calculations involving ions. So we'll practice this formula in a second. What I've got here, so this is the entropy version of Kirchhoff's equation. Recall that in the thermochemistry videos, we looked at calculating delta H at different temperatures. And so you can also do the same thing for delta S. So the delta S at some temperature T2 is equal to the delta S at the temperature T1 plus a correction factor involving heating and cooling. So cooling the reactants, perhaps, and then heating up the products is one way of thinking. It just depends on what T2 is relative to T1. Anyway, so we'll take a look at that formula. Notice that this delta Cp, this is the difference in heat capacities between the reactants and between the products and reactants, weighted by the signed stoichiometric coefficients. So here we're being asked to calculate the standard entropy of reaction for the formation of liquid water. And so I'll write it out explicitly. The delta S for this reaction is going to be equal to the absolute entropy of liquid water minus the absolute entropy of H2 gas minus 1/2 the absolute entropy of O2 gas. Okay, products minus reactants. Note that for elements, even in their reference form, the absolute entropies are not zero. They're finite values. Okay, so we need to look these numbers up in a table, and I've got them here. The value is 69.9 for the liquid water, minus 130.7 for the hydrogen gas, and then minus 1/2, 205.1 for the oxygen. And so we run this through our calculator. And so we get minus 163.4. That's going to have units of joules per Kelvin per mole. This is the same reaction that we looked at earlier when we predicted the sign, and our prediction for the sign was correct. When you're consuming moles of gas and not producing any, you should expect the sign of delta S to be negative. Here, this is a example. I'm not quite sure I understand it. Compare the standard molar entropies of chloride and magnesium ions. Well, we see that the chloride ion is plus 57 and the magnesium ion is minus 128. What I'll point out, and what I guess the answer is that those numbers are relative to the absolute entropy of H plus, which is equal to, or which is taken to be 0 by convention. So that minus 128 means that the absolute entropy of the magnesium ion is 128 joules per Kelvin per mole less than the value for H plus, and that the entropy for chloride is 57 joules per Kelvin above whatever the number for hydrogen is. Let's see. Okay, so this is one of the temperature-dependent problems. So they want us to, they give us the entropy of reaction for this, for the formation of water vapor at 298 Kelvin, and they want us to calculate it at 373 Kelvin. So we need to use this approach. I'm going to go ahead and plug in the temperatures. 373 will be equal to the delta S of reaction at 298 plus a term involving the change in the heat capacities. And then we would integrate that from 298 Kelvin up to 373. So this is kind of a tedious problem. Let's just go through it. So the delta Cp is going to be the Cp for H2O gas minus the Cp for hydrogen gas minus 1/2 the number for O2. So looking at the table, we've got 33.58 minus 28.84 minus 1/2 times 29.37 minus 9.9. That's going to be joules per Kelvin per mole. So that's the change in the heat capacity for the reaction. Now we're going to plug that in here. It's a constant. In general, it could be a temperature-dependent function. that we would have to integrate. But as of now, it's a constant, and so it can come outside of the integral. And so we're going to have the integral of dt over t is just going to be the natural log of, the final temperature over the initial temperature, 373 over 298. And then we need to plug that number in. Plug in the number we're given for this one. I'll go ahead and do that. So it's minus 44.42 plus minus 9.9 times the natural log of the ratio of the temperatures. And I'm getting minus 46.64 joules per Kelvin per mole. Okay, so that's the value that I'm getting out of this. So this is another example of essentially Kirchhoff's law, this time applied to entropy changes instead of enthalpy changes. All right, so I'm going to go ahead and stop this video here, and we'll talk about free energy in the next one.